Welcome to this talk on structured arrays, which is a very highly developed area of Wolfram language now. And what I'll do today is to give you the general framework of structured arrays and show you how they are kind of somewhat different from the usual lists that we know in the Wolfram language. And then once that is done, then after that I'll go on to the actual examples, but in which I'll have things like uh, the 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 identity matrix, the permutation matrix, the Van der Waals matrix, the Fourier matrix, and orthogonal matrices. So the idea is to give you a balance between theory and the example, just to show you how powerful this whole framework is and how well it fits into the modern way of doing linear algebra. So let me begin now by talking about structured arrays. So structured arrays are a recently added feature, and they actually help you to make things much more compact. So just to give an idea, the typical identity matrix has got 5 rows and 5 columns. But if you say target structure goes to structured, then you get back just this summary box with some indication of what the entries look like. And that's really convenient. Think about identity matrix of order 10 to the power 4, or better still 10 to the power 9. Good luck with trying to do that in some earlier version. So if you compare that to the list version over here, which is what was there all along, and it's still there right now. So this is what you would see without the target structure option over here. So the point over here is that you can either have the list version or you can have the structured version. The structured version is really much more useful. Okay, so it's not like this is the first time we've had a new kind of array in the language. Uh, in fact, going back to version 4, we had packed arrays, but they were much more for numerical efficiency, very mysterious and a little hard to figure out what they were doing. But the first formal kind of array we had were these so-called sparse arrays, and they were designed to deal with problems where you have large matrices with very few non-zero entries. So these matrices required, or arrays more generally, required that you have a sparse structure which would then encode the non-zero values and not worry about anything else at all. Okay, so this was the sparse array movement. And then a little later in version 9, we had symmetrized arrays. So you can see you can do type symmetrized array and you get back symmetrized array over here. But these were much more in line with modern tensor algebra and calculus, because in those parts of science and mathematics, one is concerned with symmetrizing objects, and in very extreme cases, only symmetric things matter. Okay, so uh, these are the kind of predecessors to the current structured array framework. Okay, so the point over here is that we have had the list structures forever, so we need a new option in 13.3 to deal with it, and that's what we just saw in the previous slides, the target structure option. So target structure is an option for linear algebra functions that allows you to decide what kind of result you want from your function. Okay, so here is somewhat terse language to show which matrices actually support target structure. Now, it looks like a big list, but there are some differences. Okay, the newer matrices like this one, Cauchy matrix or block diagonal, etc., actually have the target structure set to structured by default. The older matrices like diagonal matrix, for example, or more recently rotation matrix, will have a target structure set to kind of the list version, the dense version by default, and then you must manipulate accordingly. But you can go back and forth between the list version and other versions using the target structure option. So I think the target structure option is kind of a wonderful thing which we have had since last release, and now it's going to become even more powerful in version 14. Okay, so with that background, let's now talk about, are these structured arrays different from lists? Well, they look different, but for all practical purposes, you can work with them as you would with any ordinary list. So here's a Fourier matrix from the typically fast Fourier transform, whatever, of 28, 128 over here. And the matrix plot over here is just what you'd see with the list version. So Fourier matrices will work whether you're working with the dense version or the structured version. Okay, so there's no need to worry about will my code work or not. It will continue to work just as before. So question is, why would you want something like a structured array? Well, first of all, they definitely in general take less storage than on a list. As I think of identity matrix of size, let's say 10,000, so you need 10,000 rows and 10,000 columns to store versus just start storing the order of the matrix. That's really, really much simpler and less storage. And of course, there'll be cases where the storage is not such a big issue, but there'll be cases also where it's kind of half better in some sense, like in a symmetric matrix where you store half of it and the system figures out what the other half is. But more importantly, once we know that your matrix is structured of a particular type, whatever it might be, then we can actually design algorithms, and then they'll take less time, memory, etc., because of these specialized algorithms. I'll show you examples, where these algorithms actually work brilliantly. So put together, this notion of storage and algorithms is itself a very compelling reason to have these structured arrays in the system. So as an example over here, here's an identity matrix of size, division 10,000, so 10,000, 1,000 by 1,000. Okay, and if you actually uh, find out in the structured form, it looks nice and neat. But if you would actually do the normal of this, by which I mean convert it to a list, gosh, that's going to be huge. Okay, and if you compare storage, you're going to take 0.392 kilobytes in the first case, in the structured case, just that box, the summary box, and 8,000 kilobytes. That means that really things which were not possible, and not possible almost for silly reasons, are now working wonderfully well thanks to the structured array framework. Okay, so I think that we really have managed to get quite a lot of mileage out of this already. So then the question is, okay, about storage, how about actual computation? Well, anyone with basic matrix knowledge knows that a determinant of an identity matrix is just 1. So of course, if you ask a structured version, it'll tell you the answer is 1 in a very, very tiny amount of time. If you ask the list version, it knows nothing. It'll take almost 1.5 seconds to figure out something that anyone could have answered. So clearly structures are important in this particular case. Or if you compute the inverse, well, the inverse of identity matrix is again itself. So then that's quick, and the actual list version is much, much slower. And of course, if you go to higher dimensions, things get much, much better or worse depending upon whether you're doing structured versions or the dense versions. Okay, so the other point is that these matrices, these structured arrays, are actually, they have self-knowledge. They are self-aware. So like a bit of AI. Okay, so if you construct this permutation matrix by telling it what the cycles are over here, 1, 6, 5, and 2, 3, 4, you get back a summary box. But that matrix now knows everything about itself. But before showing you that, let me explain this if you're not an expert on permutation. So the first row gets permitted to 6 1. So you see there's 1 over here, and then the second one to 6, etc. So 6 goes 5th, etc. So the cycles are shown over here, and the permutation matrix encodes those cycles. And you can ask it, okay, what are your properties? And it'll tell you quite quickly what it knows about itself. It knows lots of stuff about itself, including what it's good for. So structured matrices are self-aware. You can query them at any point in the system and use them with great ease. Okay, you could also ask it specifically, like you can say, what are your permutation cycles? It'll just do that for you automatically. Okay, so I think that already you can see the power. You've got better storage, better algorithms, more knowledge about the matrix at any time when you query it. So the point over here is that we also have this property which you saw implicitly, that you have the property of structural algorithms. And what that does is that if you take a particular structured matrix and you try the property, it will tell you which functions it is optimized for. And in each case, that might be a long or a short list, but you will definitely get some benefit or the other. Of course, permutation matrices are very, very simple, so one should have no difficulty working out various things over here. And the other point is that it'd be unfortunate if something which should have been structured suddenly lose the structure. So let's say you do the Kronecker product of over here, then you get back another permutation matrix. So we try and preserve the structure as we move around the system and perform operations. So that's kind of almost two more reasons to use structured arrays. Okay, so the first example, let's take a van der Waals matrix. Okay, so here's the van der Waals matrix, okay, in the matrix form. Okay, so it requires, in this case, a specification of a vector, right? X1, X2, X3, X5. And it's clear way that this got something polynomial about it. And so they appear, in fact, in interpolating polynomial problems, which is how actually we use them even in the standard course on linear algebra. So then what you can do is you can take these van der Waals matrices, take some data, and fit a polynomial curve to it. So I think that this is a very standard operation, but doing it with van der Waals matrices is, of course, much, much more efficient and elegant. Okay, so uh, the point over here is that for van der Waals matrices, if you have, let's say, a vector of length 100, then storing this would be very, very easy compared to storing the full matrix of order 100 by 100. Okay, so if you look over the quantities of memory used, it's 3.16 versus 80. So clearly you have a huge saving when you work in the structured world, again in this case. Okay, so the other point over here is that your computation, like you saw earlier on the identity matrix, will typically take a lot less time. So the transpose works quickly compared to the non-structured version. If you try and do a linear solve, that works much faster as well. Now keep in mind that linear solve and other functions do have specialized support for certain class of matrices, so you don't always get the full benefit, but you can be guaranteed to get at least the same benefit from using the structured version. So uh, linear algebra is a very well developed area of Mathematica. We've been world class forever. What this does is just puts the final layer on top of the whole functionality. Okay, so now let's move on to Fourier matrices. So Fourier matrices, of course, are kind of very, very important in applications, particularly the fast Fourier transform, which actually is an implementation of the discrete Fourier transform. Okay, so there's a classic algorithm, the Cooley and Tukey, which gives you a fast Fourier transform, and it saves quite a lot of effort for you. It goes down from O of n squared to O of n log n for matrix multiplication of Fourier matrices with vectors. Okay, so we have a very nice implementation of this fast Fourier transform in the Fourier function, and it's used for um, the Fourier matrix computations as well. So clearly, these Fourier matrices are the right way to go in many, many situations. And of course, question is, why does FFT work? Well, the idea of FFT, well, there are different ways of looking at it, but here's an example which shows that, in fact, what you do is you take a matrix for which you want to do the fast Fourier transform, and you kind of, you factorize it into different parts. And these are really simple parts. They are very sparse. And in fact, each row only has at most two non-zero entries. So there are many discussions of the literature by Van Loon and people like that, which I recommend you. But basically, you have a simpler matrices which you factor into and a permutation matrix. So each step is very, very efficient, and that's how the fast Fourier transform works. Okay, so the link over here to Van Loon's work is actually quite useful for understanding this in greater depth. So I think the Fourier matrices are actually a big thing for a lot of practical applications, and we'd like to improve this area even more, both symbolically and numerically. So in a way, linear algebra lies at the heart of um, analysis and calculus, but in a very kind of quiet way. It's at the bottom of most important things. Okay, so then I go on to these so-called orthogonal matrices. So what's orthogonal mean? You have a matrix, you multiply it by its transpose. If you get back the identity, then that's orthogonal. Ortho is just right angle, so you want uh, basically a sequence of vectors which are at right angle and kind of length 1. So that's an orthogonal matrix from a kind of basically an orthogonal set, you get back this orthogonal matrix, a structured array. Okay, but the nice thing is in version 14, we not only have this new object orthogonal matrix, but we can also use it as an output from various other matrices. So in fact, our goal was twofold. One is to build a library of structured matrices, and secondly, to then use them in different parts of the system. So for example, in version 14, which you still don't have, but it's almost done, if you do rotation matrix of an angle about some vector over here, and you say target structure goes to orthogonal, you'll not get the list structure, you will get the actual uh, structured array, which is orthogonal, of course, right? And of course, you can then do a normal and look at the matrix if you prefer to do that. Or a reflection matrix has got the same kind of property, or an Euler matrix. So we have a large number of built-in matrices which will actually do this for you in version 14. Namely, they'll give back output, which is much more intuitive and efficient. And perhaps I guess the very top goal for us was we have lots of these matrix decompositions, and in each case there's a particular kind of output that's generated. So for example, QR will generate the orthogonal matrix upper triangle, but we couldn't see that earlier version. Now we can say target structure goes to structured, and it'll do just that for you. So by looking at the structured output, it's more intuitive, much more powerful, much easier to use. So I think that that's one important decomposition occurs in, let's say least square approximation, etc. And then you go the singularity, perhaps the most famous decomposition in linear algebra. Yeah, so in fact, this is, Golub had something on his number plate which said, I think Professor SVD or something of that sort. So SVD is a big thing for linear algebra, and now we can get back the structured form of SVD in version 14. So you get back an orthogonal, diagonal, and matrix. Okay, so this is really nice for people who work with these decompositions. And of course, a lot of people do. Okay, so then over here, just to do a little bit more work with orthogonal matrices, where do they come from? So for example, they come from these matrix distributions which we developed some time ago. So there are parts of system which are now becoming more understandable due to these new structured matrices. So this is a matrix distribution. You convert to orthogonal matrix form and check that in fact the inverse is equal to the transpose. And in fact, there are other properties. If you take two orthogonal matrices, you multiply them, you get another orthogonal matrix. And remarkably, even the Kronecker product of two orthogonal matrices is going to be another orthogonal matrix. Also, I think, I'm not actually sure, but this probably depends upon them being square. Okay, so there's some work going on underneath to prove these things, but we leverage that to make things much, much nicer for everyone. So I think that this gallery of examples, we began with identity, went to permutation, Vandermonde, Fourier, orthogonal. There are a few more coming. So there's symmetric, there's unitary, and there's Hermitian. So those matrices together, we have an impressive library of basic structured matrices for you to start working with.